Hi, so I'm Jeremy Gebben, work at Spencer with Lunar G. I'm not nearly as peppy as he is, so uh, so I've been working at Lunar G for 4 years. I've worked mostly on the validation layer. Um, Prior to that, I crashed a lot of GPUs as a kernel mode developer. I also worked in architecture on trying to make some of these hardware features for debugging better. I've also spent a lot of time crashing things like satellites and lasers and TVs. Um, so we'll talk about crash diagnostic layer, as Spencer alluded to. It's a pile of glue code and dirty tricks for debugging device lost. It works on Windows, Linux, and most recently Android. It it doesn't require extensions. It makes use of them if they're available, and it tries to do what it can with whatever's on your device. Tries to be fast. For real games, it's about 5% per hit. It's currently beta in the SDK, mostly because we haven't had a lot of issues come in on it. It's been out for about 5 or 6 months. We think it's in really good shape now, but yeah, please file issues and tell us how it's working or not. It's based on a tool that the Stadia team made called Graphics Flight Recorder, and kind of when Stadia ended, it was abandoned, and we picked it up and made it better. So what does it do? It tracks forward progress of what the GPU is doing and with your command submissions, and it can interpret fault information from the driver. We manipulate the command stream to add breadcrumbs or checkpoints and optionally barriers to reduce the amount of commands that are executing at the same time. And we dump out to file in YAML so that you could potentially write tools to parse a large collection of crashes and figure out how many unique crashes you have. The big limitation is we don't know what's going on inside of your shaders. We don't have access to what the instruction counter is. There's not any defined portable way to represent that. So we can tell you crashed within this draw call. We can't tell you that it was this line of your code. It's just what's available in device vault right now is limited. Ooh, wow, that didn't format good. So there's a number of extensions. They're very widely supported. My colors got lost. Device fault is the main one. That is information from the driver about a GPU crash to try and give you more information about what's going on. Device address binding report is information about all the device addresses, not just buffers, but internal driver allocations as well that are being made on the hardware. So that gives you a map of memory on the GPU, which is used to figure out what's related to your fault. We'll talk about that. The NV device diagnostic checkpoints and AMD buffer marker are breadcrumbs or checkpoints, and those tell you where in the command stream the GPU is reached before it crashes. And then AMD device coherent memory is a way to avoid GPU caches when writing out buffer markers so that you get better information after a crash when your caches might not get flushed. And all of these are getting more widely supported. And hopefully there'll be more extensions over time that we can add support for that work on a lot of devices. So let's talk a little bit about what happens when your GPU crashes. It's not quite the same as a CPU since it's a separate processor. So if you're the user, you could get a whole bunch of different behaviors depending on the operating system and the application. You could get an error dialog from the app or from the OS itself. Windows now, if you write a test program that crashes the GPU a lot of times quickly, will take away your rights to access the GPU, which is fun. You could get the application just going away, a black screen that lasts for some time or forever. You could get logged out. Kernel could panic. My favorite one is that I've seen devices where they just get very warm. That's not good. These days, we're tending more towards the top of this list than the bottom, and that's great. We just got to keep working on it. So what's happening at the application level? You do something, eventually you get device lost error back. You might get a timeout too, and you have some choices. You could restart rendering, which if you're a compositor or something system critical, that's the best choice, is do everything you can to get something back on the screen for everybody. You could exit nicely. Maybe you could save your CDL output and send it off to the developers so that they know that think things are crashing, or you could just crash, and maybe that's okay. So in the driver, there's a lot of stuff going on where the driver is monitoring your command submissions and what's happening on the hardware. So it probably has some timers in it that might time out if the GPU gets stuck. Traditionally, that was called a hang, where the GPU just stops responding, nothing happens, the screen doesn't update anymore. The timeout prevents that. There's also often fault interrupts that could occur that'll tell the driver something bad happened. And at that point, the driver has to figure out which application caused the problem. You could have 5 or 6 different programs trying to use the GPU concurrently. Only one of them caused the problem, and you want to tell it that the device is lost. For a while, this wasn't working on some systems. They would tell everyone the device was lost, and that's why like X would go away, because it's like a GPU crash, but it's not them. So then the driver tries to reset the hardware and continue on with all of the rest of the applications. That's the ideal, is that this one application crashes, the rest of the world continues on, and that sometimes is hard to get right. So why is this so hard? It's relatively new compared to CPUs, where we've had multi-processors, multi-user systems for a long time, and core dumps since before I was born and stuff like that. GPU crashes for a long time were considered a software or hardware bug, and it became an all hands on deck exercise to fix them. You wouldn't ever ship with a known GPU hang if you could at all avoid it. Also, the early use cases were these full screen games. There was no concurrency. It's just one user using the system for one application at a time. It crashes. Okay, well, they can figure it out. They can reboot, whatever. Another problem is just the nature of the beast. You have all these shader invocations. You can't really step through them all on the hardware. You have massive amounts of state you might try to save after a crash. And then there's just the nature of multi-threaded debugging, where sometimes problems go away as soon as you instrument them. Sometimes that's good, sometimes it's bad. And then there's just the nature of the IP, where some of it's not publicly available. You don't always know what all the registers are on all the different GPUs. There's big differences in the architecture in terms of tilers versus direct renderers, and then just how registers are laid out, what registers mean. The amount of information that's getting out there has gotten a lot better in the last few years. That's great too. The sad one is that sometimes debug features aren't a priority for the different teams. Like if you have a chance to do a performance optimization or add some more debugging features, a lot of times the driver teams are going to have to do the performance feature, and then debugging gets whatever's left. So using CDL now, how does this thing work? So it's integrated into vkconfig. Start it up, there's a preset for it, then go crash something, and it'll dump out messages to the console and some files to the file system, and where they go depends on the operating system. And then, like I said, this is a fairly new tool, so we need feedback on what should be better about it. And we'll talk about some of the different things it does, which are, there's options in CDL or in the vkconfig to turn them off and on. So here's an example of the log message. So it'll, with info level on, it'll spit out what's happening at startup. It'll tell you what extensions it's not finding and what that means for you. And then eventually, if you hit a crash, it'll start saying how we detected the crash. Then we timed out trying to look at got a bad value from a semaphore query. And then it'll say, oh, we decided there's an error and we dumped a file out. And then you can go look at the file, and we'll show some examples of what's in it. I guess one important point is that it tries to timestamp all your crashes, so that if you're repeatedly crashing, it won't overwrite. You might have non-deterministic crashes where you get different outputs, or you crash at different points, and sometimes that's useful to have a whole collection of crashes to debug. So I mentioned that one of the big things that it does is track forward progress. There's 2 main ways to do that. Is in the tool is we have a timer that's trying to do watchdog timeout stuff, and then we're also instrumenting the submission stream and the command stream to get past these problems where it's hard to tell from the application level if the GPU is still moving. So the watchdog timer, it just runs in the background and tries to detect if the application is still able to submit work. The assumption is that most applications will submit things periodically. I try to hit a 60 FPS frame rate. You're going to submit frequently. Some use cases you might not want this watchdog timer on, so you can turn it off. If you're using the debugger to step through code, the watchdog timer doesn't stop, and so you get false hang detection from that. Some drivers do have their own good watchdog timers, and then this one's just kind of in the way. And then you might also have long-running compute jobs where you send a dispatch to the GPU and it takes a few seconds to come back, or a minute in some cases I've seen, and that would be another reason to turn the watchdog off. And we also change how your commands are submitted. So you make one VKQ submit call. You might have a number of command buffers in it and a number of semaphore waits. That gets broken up into these individual submissions. And the reason that's done is so that a timeline semaphore can be signaled after each step of the submission. And that helps us identify which command buffer caused the hang. So in this example, you have some wait semaphores and then a few command buffers and then some signal semaphores. That gets split up so that we can detect if you hung waiting for a semaphore, that's a different problem than if it's in a command buffer, and then we want to know which command buffer the hang happened in. So that automatically gets done by the layer for you. Then within the command buffer, we have checkpoints to try to determine which command the hang happened at or the crash happened at. There can be multiple commands executing in different parts of the pipeline at the same time. So you end up getting a range of possible commands for the hang. So we write these checkpoints after interesting commands such as draws and dispatches and copies, and we write them at both the top of pipe and bottom of pipe stages so that you can determine the range of possible commands for the hang or crash. There's two ways that this is implemented. With AMD buffer markers, we have to write before and after each command that we want to instrument. And the interesting thing about this extension is these writes always happen. So you could, in theory, if you wanted to do this on your own, you could just put these buffer markers everywhere and you could get the entire state of what's happened in the GPU. That's useful because it's really simple. You wouldn't have to do the timeline semaphore trick. We'll talk about why that happens with the other extension. But these writes are affected by caches within the GPU. So AMD added made this other extension called device coherent memory that bypasses the caches for writes. And that way you get much closer to where the actual execution was when you crash. So this is one set of trade-offs. The other extension, NV device diagnostic checkpoints, it works very differently. So there's a single write that gives you values for both the top and bottom of the pipe. And then there's a call that you make. This one just writes to a buffer. So you just have a location and a buffer, and you can go back and look at it and figure out how far you got. This one, you have to call this get queue checkpoint data to figure out where the GPU was when it stopped executing. And what you get back is just the checkpoints in the most recent command buffer is what it looks like to me. It's kind of poorly specified, but that's what it looks like. So you won't get back like if your command buffer finished executing entirely, you won't get anything back. So you don't have a global state of what happened, but you get very accurately within that one command buffer where you were when it crashed. So it's a different set of trade-offs, and this is why the layer also has that timeline semaphore trucking mechanism, so it can know which command buffer was in flight when the crash happened. And so the output of this is it'll dump out the region of commands within the current command buffer that are associated with the crash, and it'll have these two markers that says the last command that we know is complete was that debug utils label, which that's not actually going to execute on the GPU. So yeah, that's going to complete. And then the last one that started was this draw indexed, and then there might be any number of commands in between there where, depending on how much is in flight, you might have a few commands or hundreds. And so then you have to look through this range to figure out why it crashed or what's causing the crash. One thing that can help with that is the device fault extension. That's giving you essentially information about page faults on the GPU. And it'll give you some additional information about what type of access it was. And then vendors can also provide their own proprietary information in the extension, and there's not really any specification about what's in there, and it varies quite a bit from the people who support it. So we just dump that to a file, and you can go look at it and try to figure it out. But the main fault information, we can look at the output of the device address binding report extension, and that can give you information about what is allocated in memory near the faulting address. So we have some examples of that. So buffer overrun, here we have a fault, and the faults all have a range because there's only so much granularity in the hardware about where the faulting address is. So in this case, the range starts at A600, and that happens to be the end of a device memory region. So that device memory region is still bound. So that means that you probably read off the end of that region and got a page fault that way. Use after free, here we have a fault where the begin of the fault region lines up with the beginning of a device memory region that got freed. So it's no longer valid, it's no longer mapped on the GPU. So probably you freed this memory too soon. And then if you have a bad address, here we have like this was dead beef. So that's obviously not a real address, and there's not a matching record. So then this is a case where you probably forgot to program a pointer into some data structure, and the GPU tried to read garbage. The last feature of this that we're going to have this extension or this layer that we're going to talk about is sync after commands. This is inserting pipeline barriers after draw calls and dispatches to try and reduce how much concurrency is on the GPU. There's one application I was working with where there's a crash and there was 180 commands in progress on the GPU. And so that window of what you had to look through was huge. And then just adding pipeline barriers after each command, we got it down to one, and it was much easier to figure out what to debug on that crash. This also can make your crashes stop reproducing. That most likely means that you were missing a barrier. You should go look at sync validation and figure out what barrier you actually need in your code. This also only works with dynamic rendering, and this is why. So you have a begin rendering region. You can't do a pipeline barrier within a render pass or within a dynamic rendering region. So the layer will stop that region when it wants to write a barrier, do the checkpoint and the barrier, and then restart the rendering region. This is possible to do for render pass. It just hasn't been something I've had time to do yet. And so then that pipeline barrier will prevent anything else from executing on the GPU while that command is running, and that can help you narrow down where it's crashing. Last thing, as Spencer mentioned, this tool supports debug utils, and it's very helpful if you have a crash that's associated with a buffer, and you know what that buffer is, or you know what part of your command stream you're in. That can really help you figure out how to narrow down your crashes. And that's it. So thank you. Any questions?
What is the performance impact of using this? And is somebody supposed to use this after they've discovered the crash? So like, should they proactively instrument?
So the performance impact is about 5% on like a AAA game trace. So you could run the game and do a lot of testing with it. I would say it's something where you'd want to use after you know that the application is misbehaving. You turn this on try to do the same thing again and then get the crash dump out that way rather than running it all the time. I mean,
Got it. So you discover the crash first and
Yeah.
then turn it on.
yeah.
Thank you.
Just a quick comment, because so I work on the Android platform, and we obviously use Vulkan in the platform.
Yeah.
And there are times when we encounter VK device loss, and as much as to our partner chagrin, the SIPs and the GPU IP vendors want us to handle device loss, and we're like, it's the platform, so we crash, and we crash hard on purpose because we want the drivers to operate the way they're supposed to. So I just, in the decision tree when you were talking about before, like from an application perspective, yes, doing nice things is good for your users, but sometimes the right answer is to hold the line and not like introduce this nebulous, oh, we'll try to get by because the hardware's behaving badly.
Yeah. I worked on Android for a while, and at one point we were trying to reset and recover, and then there's like, you get a log file and there's like, oh, there's been 5 GPU crashes in this log file before we hit the thing that reported the bug, and it's a trade-off. But yeah, you have to enforce it somehow, I guess.
So just to Mark's point, the working group hasn't seen this proposal document yet, but there is a revised device fault extension. One of the things in there is the ability to ask that faults that the driver might be silently consuming become fatal.
Okay.
Which is potentially a useful thing. You'd never want to turn it on your live app, but it's potentially a useful like forcing function for fixing your bugs.
Yeah. Okay. Oh God.
I didn't ask you. I saw your dry run. I didn't think about this before. If I blue screen to death, how is it? Is it logging constantly, or how like if I blue screen, the whole machine shuts down? How are you? Will I still be able to find my log after?
Maybe. It's trying to write out. It's using unbuffered I/O, and I know you can get a good dump file out when you're getting logged out of X. I haven't had a device that's blue screening on a GPU hang in quite a while, so I'm not sure. But the layer's trying to write out as best as it can, but you're kind of at the mercy of the OS if the whole system's going down.
So my question, have you seen cases, or do you have some example where turning on CDL actually made a bug or a crash go away just by splitting up the command buffers, or some other, like, is it safe to use it, or do I risk to obfuscate some existing problem with it?
I think the sync after commands feature where it's adding pipeline barriers, that I've definitely seen that make crashes go away. The rest of it I haven't. And that feature is not on by default because it is so intrusive and because it doesn't work with underpasses. So it's kind of a try this as a last resort feature, which is how GPU hang crash debugging tends to go, is try everything until it goes away and then figure out why it went away.
Any other questions before we close? Okay. One more.
Yes, I would like to know how do I detect now this out of bounds access? I'm sure I tried with NVIDIA Aftermath to reproduce this. Do I need to enable CDL now?
CDL will tell you, so the device fault extension would tell you that you got an invalid access. And then with the range of address maps that we get from the device address binding report extension, that could, let's see. Yeah, so buffer runs. So this would be out of bounds. This is how it would show up in CDL: is you have a fault at address A600. And the nearest address record that we found is ends at A600. So that would mean that you went past the end. This right here, if you had a label on this buffer, a debug utils label on the buffer, we print it out there. That's the best we can do. We can't tell you what shader instruction. That's when you have to start using GPU AV. So this is kind of a first line tool of trying to figure out where in the application is crashing so that maybe you can find out what part of the application is crashing, make a short trace with graphics reconstruct, and then enable GPU AV on just that short trace so that you can reproduce it in a timely manner.
Okay, thanks. I need AV, yeah, assisted validation.
Like Spencer said, there's no silver bullet. You have to use a lot of tools.
So any more questions? Okay, if we could thank our speaker again.
Thanks.